Welcome to today's GTMA-sponsored webinar, Using Crash Data Analysis to Develop Network-Level Road Safety Programs. We are pleased to have today as our presenters Scott Jones with the Utah Department of Transportation and Stephen Reed with the Virginia Department of Transportation. Scott and Stephen are some of the best safety analysts that we have working for transportation agencies today. Both are using innovative tools and data sets in order to improve the analysis of the safety on their networks and developing strategic safety plans and determining how best to invest highway safety improvement program funds. And so today we have an opportunity to hear from both of them. And given the amount of time we have, I don't want to spend a lot of time in background. You've all had an opportunity to kind of read what their focus will be today. But we are very fortunate to have both Scott and Stephen as presenters today. You have an opportunity to ask questions over the course of this webinar, but we're going to hold all questions until the end. So, utilizing the question button or tab, we would ask you to type all of your questions and send them in. I will organize them over the course of the webinar, and at the end we will jump right into questions, answering as many of them as we can before our time runs out today. And so with that, we will turn the time over to Scott Jones with the Utah Department of Transportation. Scott?
Thank you. Good morning. I'm going to talk a little bit this morning about some of the data that the Utah Department of Transportation has collected, and then ways we are displaying and analyzing that data. For those of you who have seen our introduction before, I apologize. I will go through this quickly, but I think the background is helpful for those who aren't familiar with what we've been doing. In 2012, UDOT embarked on an effort to collect all roadway and roadside attributes with a single vendor driving the roads in a single pass. To give you an idea of the scope of this project, the state DOT maintains roughly 6,000 centerline miles of roadways, and including ramps and collectors, and this data collection encompassed the entire state highway network. We contracted with Manley Communications. They chose to use Lidar as the primary collection tool, as well as some high-resolution right-of-way imagery as part of the data collection process. I will mention that after the successful completion of the 2012 data collection, we've just completed a 2014 round of data collection, and we do continue. So we plan to continue on a 2-year data collection cycle into the future. To give you an idea of some of the roadway and roadside attributes we've collected with this project, this is just some features here describing we geospatially located all of our barrier, our shoulder and our shoulder width, lane lines, lane width, sign faces, including a description of the foundations and the connectors, walls, wall heights and locations, median width, surface areas, location of rumble strips, all the pavement condition information, roadway geometry. And then in the urban environment, of course, things get very complicated and complex with intersections, other pavement messages, signal head locations, signal cabinets and power pedestals, drainage features, curb and gutter. I think I've mentioned everything there displayed on the picture. So we took all of this data that we've collected and we've created a data portal. This is fashioned after the data.gov website. We've got our own for Utah. You'll notice on this screenshot of the data portal, we have several ways of accessing the data. I will highlight two of them quickly. We have a data download tab, and then I'll talk briefly about UPlan. So our data download tab looks like this. If you click on that tab, you can search for assets in an open search box, or you can browse the different asset categories there by categories, predefined categories that we've got there. You can download these data sets as Excel spreadsheets, shape files, KML, KMZ, data dictionaries, and the metadata behind the data collection process, and everything we could think of that we could provide is available here. And this is all available to the public as well. You're welcome to browse this at your convenience and take a look at what we've got. We also display the information graphically in UPlan. UPlan utilizes the ArcGIS online data portal. We recognize the need to display this geospatially as best as we can in order to tell the story. Oftentimes just data tables and databases are not only boring, but it's hard to tell the story if it's not visual, and UPlan helps us visualize the data in an online mapping format. This is a poor attempt at explaining what a UPlan map might look like if you combine several data layers together. One of these data layers is a safety index that categorizes a roadway based on crash data. We've also put in the barrier layer here, walls, pavement messages. The green dots are locations where signs. The blue is bridges. Rumble strips are displayed here. So you can combine the different data layers as a user any way you want to display and customize those images on the map. So with that background, I'd like to talk a little bit about what we've done with shoulders. We did a systemic analysis of our state network to identify where we have deficient shoulders and where we might consider the first prime locations for doing shoulder widening projects. Utah, by lane mile, is a fairly rural state, and we've got a lot of two-lane rural roads where the shoulders are in a variety of different conditions. Here's some examples on these pictures here. What initiated this project is one of our UDOT regions asked us for some federal HSIP safety funds to widen shoulders on a certain section of roadway, rural roadway, where they felt there was a safety concern. And as the program manager for that program, I was concerned whether we were taking a holistic approach to looking at the entire network and truly prioritizing our greatest needs for where we should be spending our money to widen shoulders. Just as a teaser, the image you're currently looking at is the section of roadway where that region request came from. In doing our analysis, we found many of our two-lane rural roads that had a lot more deficient shoulders than what you're looking at in this picture. So let me tell you what we did to embark on this project. We first identified several different data layers that we wanted to include in our analysis. One of them was, well, let me proceed with, I have a slide that talks about each of these data layers, but you can see them listed there that we identified as potential sources of information to help prioritize our shoulder widening. I'm not going to read that to you now. So first of all, we looked at our shoulder inventory data. This came right from the Manly data collection effort that we did. This is that shoulder analysis displayed on a UPlan map. And as you can see here, you click on a segment of that roadway and you get a pop-up window that describes the right shoulder on this section of roadway. The shoulder width is 0 feet. of width of that shoulder, and the edge type is a UBC, untreated base course. So this section of roadway has no shoulder. We have this type of inventory information for our shoulders through our entire state network. We also use speed limit as a contributor to weight priorities for shoulders. This UPlan layer displays for you all of our speed limit signs that are along our network. We can use these signs, obviously, to segment where the speed breaks are on the roadway and identify speed limits throughout the network. We also looked at our crash data, both runoff roadway departure type crash data, as well as crashes that involve bicycles. We identified bikes as one of the roadway types users that would benefit from a wider shoulder, and so we wanted to make sure that we accounted for hot spots that may be occurring where bikes are being hit by vehicles. This part of the analysis, we found that there were many more areas with roadway departure crashes than bicycle involved crashes, but we used both as a weighting factor in our analysis. We also looked at our primary bicycle routes. Utah is a destination for some of these national touring groups that will come and use some of our rural areas for biking, as well as in our urban areas. We have partnered between our regions, our local governments, and our MPOs to identify key bike routes that people are using for recreation and commute purposes. And we call that initiative UCATs that are mentioned here on the screen, on the slide. Here's an example. Here's a UPlan map layer for some of those key bike routes that have been identified through some of these initiatives. I didn't include the legend here. Obviously, some of the symbology here represents different types of users and intensity of bike use, but that went into our shoulder widening analysis as well. We also looked at our primary freight network. This is off, although this map shows interstate, we didn't identify any interstates that had deficient shoulders, thankfully. So we used the primary freight network on the off-interstate system to say if this was a primary freight corridor, those big trucks have a greater need for shoulder treatments, for the ability to recover, as well as to pull off the road if they are disabled. And so we use this primary freight network as a contributing factor in weighting for our shoulder analysis. We also used proximity to transit stops, and so the theory here is connectivity between different modes of transit, specifically in this case with pedestrians, bikes, and transit, and they're making the connections between the modes of travel, benefiting from good shoulder treatments. So this slide pretty much summarizes how we combine these data layers together. We looked at our pavement sections. We identified really quick the need to remove sections of roadway that already had existing curb and gutter. We did this for several reasons. Obviously, a shoulder widening project can get a lot more complex if we end up having to buy right-of-way and shift curb, gutter, sidewalk, drainage features along the roadway. And seeing as how we were focusing primarily on just shoulders, we removed sections of roadway that had existing curb and gutter. And that curb and gutter was already identified again in our Manly data collection effort. So it was easy to remove those sections of roadway. We also removed sections of roadway that already had shoulders that were over 6 feet wide, recognizing that 6 feet in some design criteria are still deficient, but for our purposes, we wanted to identify roadways that really didn't have a shoulder that needed some type of shoulder treatment just to get it started. And then we also removed areas in the urban area that had parallel facilities that did have shoulders. Again, the idea that we wanted to focus on those true needs that were unique and isolated. Some of the weighting criteria we used to identify where we needed shoulders, we talked about the speed limits. We used AADT, truck volume, the existing shoulder width, obviously, and whether there was parking adjacent on the roadway. We prioritized these. We talked about the freight routes. We talked about the bike routes, bike crashes, run off the road crashes, speed limits. I want to talk a little bit about, I didn't mention the missing link of the bike network. We did talk about and prioritize sections of roadway where there was adjacent sections of roadway that already had sufficient shoulders, and there might have been a little gap in the roadway where the shoulders were deficient. It would be a quick win to finish that corridor and get that little section of shoulders completed, so it completed the network. And then we also talked about the transit, prioritizing their transit stops and that connectivity. So this is an output to our analysis. This is one of the corridors that was identified and prioritized. I'll show you a more complete list in a moment, but I wanted to, again, demonstrate to you what kind of analysis and weighting factors we used. The weighting factors, of course, can be adjusted depending on what we wanted to focus on. But this is an example of State Route 37. And how it ranked and prioritized based on those factors we talked about. This wasn't a freight route. This was a high bike use route. There wasn't any bike vehicle crashes, but there was a fair number of roadway departure crashes. Each of these scales on this scoring is 0 to 5, excuse me. This was a fairly high speed road. It linked to other routes that already had sufficient shoulders, so it completed one of those networks, and it was near some transit facilities. And so this section of roadway ranked very high. Rudimentary cost analysis here for this section of road for the areas that were deficient on the shoulders is $1.7 million. Here's a map, again a UPlan map of where we prioritize these top locations statewide, and there's some color coding here for how they ranked on that score from the. So this is basically the first $100 million program, if you will, of where to prioritize those projects. One of those sections on that map you previously looked at was US 40, and I wanted to mention this route specifically because a significant portion of US 40 showed up in our analysis, and we thought this was really interesting. It's a pretty isolated road in the rural part of eastern Utah over some pretty treacherous mountain passes, and most of this road doesn't have any shoulders. And one of the reasons why this road as a network appeared at the top of our ranking was because it hit all of the key features of our ranking criteria. High speed, it's a freight corridor, lots of crashes. It's designated as a primary bike route. There is no alternate facilities in this area for transportation. And so you could see how the way we scored and chose to rank favored rural roads like this that were heavily used by trucks. By tweaking that ranking criteria, we could find ways to better optimize this if we didn't want to focus on roadways such as this. So here's our final list that we prioritized statewide, and we created this this list that we are sending back to our regions as this is what we prioritized in our analysis of the top candidates in the state to widen shoulders. Please get with your local people and let us know which of these you'd like us to consider for funding. Lessons learned in this process. You obviously, first of all, have to start off with accurate data. We found as we went through this several sections of roadway that we had to throw out of the analysis because when the data was collected on those sections of roadway, they were under construction or otherwise had some temporary traffic control set up. So the roadway features that were collected at that time didn't represent what's typically on those sections of roadway. Some of the sections of roadway came up as having no shoulder because traffic was shifted onto the shoulder at that time to accommodate construction activities. As with any process such as this, when we handed the list back to our regions, we had to remind them that this wasn't the final outcome of the process and that some ground truthing had to take place in order to get buy-in and to confirm that what was concluded in the statistical analysis actually bear fruit on the ground. And then we did find out, especially as we considered what weighting criteria to apply to the different factors that we considered, some subjectivity is unavoidable here. We did create a process that's reproducible, but somebody else's idea of what ranks higher than another factor certainly could affect the output. So I just want to finish by mentioning we're looking at other systemic safety tools and models in order to feed all of the roadway data that we now have available to us. And one of those tools that we are currently populating with all of our roadway data is the usRAP safety models. usRAP developed something they call a Safer Roads Investment Plan, where shoulders are only one of 40 different safety mitigations that that model proposes as an output when you feed in all the roadway attributes that's required for that model. And so we're excited to see the output of that model. We should be done by mid-year with that effort and not only compare it to what we've done here specifically with shoulders, but to see how shoulders rank with other safety features that we may be considering are needed in the future. Another benefit of the Safe Road Investment Plans is it gives you a benefit cost calculation, and it helps rank and prioritize, as I mentioned, all of these safety features in one output. So with that, I'm done with my presentation.
Scott, excellent. A lot of good questions, and we'll get to those in a few minutes. But excellent presentation. All right, we'll now take just a moment to switch over to Stephen Reed's presentation. Very good. All right, Stephen, you're up.
Thanks, Rob. Appreciate being here today. As way of introduction, I did want to say that as I started my career after college almost 3 decades ago now, I was first designing roundabouts and pedestrian malls or town centers in England, and that's when I got excited about safety and went back and did some graduate work in safety. And so not that I'm going to go back 30 years with my presentation, but I do want to talk about, in a roundabout way, walkabout way, where we've been over the last 10 years here as an agency. I came into the safety program from one of our districts about 12 years ago, and how we've evolved over time to look at different safety issues. So I'm going to talk about how we've used data a little bit over that period and then bring it back around to how we've focused on roadway departure, in particular, here in the last few years. As with all states, we're required for our Highway Safety Improvement Program to develop a strategic plan. And ours is very similar to many others. We're in our second round. We have had 2 of these developed, and we're in a plan now that has a horizon of 2016. And as you can see, to work any good plan, you have to have a mission, goal, and targets. And these are similar to what you would see in many strategic plans, with goals to have deaths and serious injuries in the next 20 years. Our plan baseline was 2010. And that equates to about a 3% reduction per year. So there are many organizations that have kind of used that goal and target, including AASHTO and GHSA and many others. And again, our plan is not dissimilar from others. We reduced, our first plan had 16 emphasis areas, and we reduced it down to these essential 7. And as you can see, as engineers and planners, we're primarily focused on the top 3 and using the number 7 in order to do that with the limited resources that we have. However, I will say that part of our attempt and focus is to work with our partners that are dealing with driver behavior of occupant protection, those that are impaired or drugged, and the younger drivers. It's interesting to note, however, that even through the first few years of this plan, we have seen great gains in that driver behavior area here in Virginia. With being a secondary primary seatbelt law state, we have seen reductions in those that are unbelted. Our impaired driver fatalities and serious injuries are going down, as well as our young drivers. Interestingly, with young drivers, we're seeing a shift in our emphasis being from those that are 15 to 18 in their first years of driving to those that are 19 to 24, those that have had a few years of experience and feel that they are the greatest drivers. So what we've done to implement our plan, it's been, we're essentially in the middle of it, wrapping it up for another update next year, is to take that statewide strategic plan, working with our partners, and try to develop district highway safety plans for our 9 construction districts that we have here at VDOT. And so we're trying to not only have our districts be more engaged with the other non-engineering partners, but also to focus on what are the specific issues within their district. And this is nothing new. It's been well done by others in Minnesota and other states. But we felt this was a good way to have our district safety personnel in traffic engineering and design and planning to take ownership of the program. I will say we are a decentralized state in the sense that they do have most of the all of the responsibility in delivering projects and working with those local partners, with the intent that we do produce and program, very good safety projects. So a decade ago, we were highly driven, since we only were receiving about $10 million a year from federal Highway Safety Improvement Program funds. We were very driven on finding the right spots, which is absolutely needed, but we tended to be focused on intersections because of that. And so we worked hard to try to look at what Scott was talking about, more of a corridor approach in terms of signalization and roadway departure with the guardrail, shoulder widening, and rumble strip combinations. We are not blessed like Scott, I believe, to have as many good shoulders that we could just go in and pave. And so we'll be talking today about how we're moving, as is federal highways, towards more systemic, lower cost treatments. Paving shoulders is not an inexpensive enterprise here in Virginia with very marginal gravel, if you will, built up shoulders to work with. So we've been working with our district folks using this sort of umbrella approach with our strategic plan now for several years. And the intent was to get them good highway safety planning data for our emphasis areas. And you can see there roadway departure, intersection-related, speed-related, and bike and ped. And although our plan does not identify non-motorized crashes as an emphasis area, each of our other areas are actually intertwined with strategies that address those issues, whether it be related to crossing at an intersection or driving along a roadway departure that has roadway segment, rather, that has roadway departure and speed-related issues. And so we've been working to improve how do we share that information over the last 4 or 5 years as we've moved from a legacy system that was mainframe-driven linear referencing system to a more GIS system. And that has required some of the steps I'm going to get into. But for this slide, the screening that is necessary initially from the district's point of view is to look at all of these data layers and identify actually where they have ongoing maintenance and construction projects. And so I believe Scott mentioned that as well. That's really one of the key first steps, is applying that local knowledge to see what is already programmed here in Virginia, that we have a 6-year horizon for our construction program. And then after that, they would, the safety-focused folks, primarily in traffic engineering and planning, would form the teams that are needed with our location and design folks and so on in order to conduct the detailed safety assessment and design that would be needed, with the intent that they would prioritize what they see as being the issues in their district and submit those for our concurrence. And so at that point, those project proposals are submitted on an annual basis to us in central office, and we help to balance the funds between each of the districts with some spending targets. One of the first things that we did in order to help the districts develop their highway safety plans is develop what we call a crash tree. And again, this is another good idea from one of the states that starts with M, who has done this down to the county level. We developed these district crash trees, and starting with the VDOT maintained system, of which we maintain 85% here in Virginia, with about 60,000 centerline miles of highway. We have our VDOT system. So the green to the left is our interstate system. In the middle is our primary or state system, as it would be called in many other states. And then on the right in the blue is our secondary system, which is our county roads. And so for each of those, the first decision was for our primary was whether or not it was divided or undivided. And although we had a number of lanes, and although while we had that for secondary, the preponderance of the centerline miles is 2-lane roads, right down to the subdivision cul-de-sac. So for our primary system, we pulled our number of lanes out of our inventory, and then we started to look at the distribution of crash types, starting with the roadway departure crashes, and then adding the intersection crashes. For roadway departure, we looked at the crash reports to determine the crash types, which are the 6 types that are right under there. And then below that, we posted the percentage of those that are on curves, which in many cases was quite astounding, actually, with it being about 50-50 in some of our districts. For the intersections, we needed to look at our database for intersection traffic control, and this was an interesting exercise for us. Being decentralized, we did not have a central repository of where we had signals, and in particular in our more urbanized areas, we're adding many signals each year, and so that is a moving target. And so what we ended up doing to define intersection control was take information from each of our districts and actually look at the crash reports in each year for those intersection nodes to determine if the police officer recorded that there was a traffic signal present. And thereby we could impute A, that there was a signal there, and B, that when the signal might have been installed. And so looking back over the last 10 years, we were able to get a fairly good representation of where we have signalized traffic control. Now we're approaching about 5,000 signals on our network. So while we were changing from having this legacy sort of mainframe crash and inventory system, we were able to take the data sets out of there and start to work with crash frequencies. And so as Scott did for his shoulder work, we started back with looking at where were our emphasis area from our strategic plan crash frequency issues. Our old legacy mainframe generated reports for intersections and roadway segments that had an above average crash rate using the critical crash rate method. And so as we were transferring to a completely GIS-based enterprise system, we went back to a frequency method. And our approach was to look at those intersections and roadway segments within each county. And so what we did was we percentiled the total crashes and the severe crashes for those at both intersections and for the roadway departure, speed-related, and bike and ped. And so for all but bike and ped, we tended to look at the top 85th percentile for the route length within that county or the 250-foot radius around an intersection node. For bike and ped, we quartiled those so that we could get enough frequency in each data range to look at which routes had those non-motorized crashes. So in a sense, we sort of set some priorities for our district staff to look at. The top priority was the top percentile, typically the 95th percentile. And then the second priority was typically the 85th to 95th percentile in terms of being the priorities for those districts. The next year, we took the data and started to talk to the districts about working with their safety partners. And so we took the same data and we actually overlaid the proportions of the different driver behavior emphasis areas. And so you can see sort of hazily there for our intersections, we created a pie chart of the unbelted DUI, young driver, and speeding crashes of those intersection crashes, and then bar charts for each of those roadway segments with roadway departures, and created data-driven maps for each county that you could zoom down into with the PDF for everyone in the district to be able to see that and to share that with their partners. So we thought this was a good place for our engineers and planners to talk to their partners as they were meeting with them on a regular basis anyways. The next year, we started to work with ArcGIS Online that Scott also mentioned with their data set, and we started to make interactive maps of the same information. And this allowed us to present not only the driver behavior, but also the collision types as a pop-up information for each of the segments and intersections. So with the interactive map and, in our case, a password into ArcGIS Online, both our districts and our partners were able to look at the issues that they wanted to prioritize and target. So while this was all going on in terms of frequency-based data analysis and presentation and distribution, we were busy generating safety performance functions using the new methodologies that were being published through research to develop the Highway Safety Manual, and also the safety analyst software that was being developed through a pooled fund study at the time, and is now FHWA suite of tools for safety. And so we began about 6 years ago, to develop safety performance functions for our rural two-lane and then our intersections, and moving into our multi-lane facilities to develop those segment versus intersection SPFs. And for each of those SPFs, we have a performance curve for total crashes as well as for fatal plus injury crashes. Here's a couple of examples of what we have for performance in Virginia. Rural multi-lane divided is more of a curved type presentation than the linear one that is the default now in Safety Analyst. And you can see the different curvature that we have in Virginia for rural four-leg signalized intersections as well. So with this information, we're able to essentially normalize for traffic volumes and determine the crash frequency per mile or the crash frequency within that 250-foot radius around each intersection node. Any existing traffic crash history that is above that curve is considered to be a location that has potential for safety improvement. In essence, what we would attempt to do is to reduce those crashes so that they are below what is normal or average for that given segment or intersection site subtype. Since we have been developing a more robust data set for our crashes, as we were finishing those safety performance functions, we decided to look at 3 years of data and actually look at the cross-tabulation of those sites that had a total crash PSI greater than 0 and a fatal and injury crash PSI greater than 0. And so in essence, our attempt was to find where do we really need to target our resources. And so as you can see here, we looked for those sites that had more than 2 years of identification of being above average with both intersections and segments. And so these maps were developed and distributed to the districts, essentially giving each district the top 100 sites to look at for intersections. Here's a screenshot of of the district in the western part of the state. And you can see with that information, you can mouse over the intersection, and the pop-up will give you the volumes, the crashes, and the ranking and the PSI value for that location. One thing that we have in Virginia, since we do maintain all those roadways, is very good traffic volume data, which allowed us, to generate both those PSIs and then give us that information to post back for diagnostics of the site. For roadway segments, we were able to find, many of those locations based on the inventory links of where we had above average total and fatal plus injury crashes. But as you can see, there's a lot of small segments there that can cluster around each other, but some of them might be dispersed and disassociated with any other ones. And so what we decided to do was look at groupings of those segments that were identified to determine whether or not we were given routes within the corridor, going back to the old frequency-based method that we had to identify for roadway departure and speed and bike and ped. We thought, let's identify those routes within a county that had a high proportion of their length that was being identified as having a targeted safety need or that PSI greater than 0. And so here you can see the routes that were identified in a similar area. However, although we had these long route segments identifying roadway departure, speed, and bike and ped, and we had our intersections both for frequency and adjusted for volume, we knew we needed to get a little bit more specific, in particular for roadway departure. And so, like many states, we are a focus state for federal highways for roadway departure, with having over 60% of our fatalities being from those that depart their travel lanes. And here's just a snapshot of the roadway departure issue here in Virginia. It's very dispersed. So each district has about 1,200 miles where we have most of our roadway departure crashes. And they're randomly distributed. If you look at this statewide, it ends up being about a third of them are on 3/4 of the network. In most cases, that's the rural 2-lane, low-volume roads, our secondary system. And so we were grateful to have Federal Highways come with their roadway departure team and work with us to develop a methodology, as they had done with probably a dozen other states, to identify how do we better target countermeasures for roadway departure. And so this was essentially the approach, was to move from our traditional and corridor higher priced countermeasures to some more systemic lower cost countermeasures. Of course, not forgetting those higher priced ones like shoulder widening, with the intent that things would move, as they did for rumble strips in our case on interstates, to being more of a standard and policy decision in terms of implementing those countermeasures and treatments on a broader extent of our network. So Federal Highways has now developed a lot of resources and tools on their website. If you search for systemic there, where they talk about the approach and provide tools and help from what has been done in several other states. Primarily looking at, let's target those different roadway departure crash types, in our case, for systemic. What are those risk factors? And then screen the network based on that to prioritize where are locations that we really want to address the problem. The countermeasures that are selected come out of identifying those crash types and risk factors, and that will hopefully help us to prioritize projects moving forward. So what do we have for lower cost roadway departure countermeasures? We have to provide driver information. So these list here is probably not new to you. It's a standard fare, but as you can see, these are countermeasures and treatments that can be installed fairly quickly and easily, although we do have some issues in Virginia with a lot of prescriptive right-of-way and our secondaries only having 15 feet on either side of the center line, and so we need to primarily focus on some of this driver information that we can put either very close to the paved roadway or on the paved roadway. Driver attention. Here is the suite of countermeasures that we were targeting, primarily looking at the rumbles, where we could put those, raised pavement markings, and wider markings, as well as messages and other feedback initiatives. And finally, how do we enhance vehicle stability? There's been a lot of work recently with states using higher friction surface treatments, whether or not that is with their overlay program or with applying the special epoxy-based friction course on those curves and intersections that deserve higher friction. And finally, the pavement wedge there, which is called safety wedge for many folks, providing 30 to 40 degree slope with the paver, so that if the shoulder was to become rutted or washed out, that folks could recover if they drifted off the edge of these narrow secondary roads that we have. And so this plan involved looking at those crash types, setting a crash threshold for our locations, and then looking for those locations along each corridor so that we can prioritize and study those in more detail. As Scott mentioned, much of this information does need to be ground truth before it's ready to be developed into a project. In our case, we're trying to get the district to think about not only safety, but also the construction and maintenance projects that are ongoing that overlap with these locations. And so for each countermeasure, Federal Highways contractor has developed a table like you see here, where we've defined the segment length or the length of road that we're screening the roadway for that targeted crash type, whether or not we wanted to break that down by volume range. So, for example, we set a threshold for rumble strips to be 4,000 vehicles a day, and said that any road that had a roadway departure problem, center line or run off the road right, over 4,000 should be reviewed for rumble strips. And then we looked at a crash threshold for those that are under that volume threshold. And then we looked at our roadway inventory in terms of what were our data needs to help refine the filtering for these countermeasures. And so you might not be able to read this screen capture from the spreadsheet, but suffice it to say that we had 16 or 17 different countermeasure packages, and each of those were categorized based on functional class and ownership as to where it is. So we had a rural versus urban designation, and then VDOT maintained and owned versus non-VDOT. And so from that window screening of each of the roadway segments in the inventory, we were able to identify the begin and end mile point for each of these treatment packages, and also the number of crashes that were found in that 3,000 foot to and longer segment is what we ended up using. So with each of these, we're able to find those segments and also identify whether or not we had one of our PSI volume-adjusted segments that overlapped. And so we've set up the spreadsheet in our maps to indicate that, as well as provide a tracking tool to determine when that given roadway corridor was investigated and reviewed, and whether or not any of the treatments were recommended for a project. And so excuse me. Here is a table showing some of the data elements that we're able to use. Now, in our case, our shoulder information was not as accurate as what Scott was able to get out of Lidar. In fact, we had to go back to our old legacy data that essentially said the shoulder width, which was a combined pavement and gravel shoulder of width, and identified those that were greater or less than 4 feet as our screening methodology for shoulder rumble strips and shoulder widening. For curvature, we have been able to procure both horizontal and vertical curvature from our pavement management vendor, and so we were able to identify some fundamental point of curvature information and radius information for our primary interstate routes. However, that is only a small proportion of what we were analyzing for this initiative, and so we ended up using the police report for our curvature. However, that is good information for ground truthing and for using for our field roadway safety assessments in terms of assessing Chevron needs, in terms of MUTCD requirements, and so on, and where, for example, to put high friction surface treatment. For guardrail and barriers, we did not have the accurate median type and width. It tended to be on very long segments with very small minimum widths and very large maximum widths if they were divided. And so again, we went back to the police codes to identify cross over the median issues for that. And similarly for guardrail, while we do have a database for guardrail on our primary and interstate routes, because it was not full coverage, we again looked at the fixed object hit for our guardrail issues in terms of installing that countermeasure. And so from all of these information, we were able to develop those layers for each countermeasure. And you can see some of the longer segments that are popping up are those rumble strip corridors that had greater than 4,000 vehicles a day, as well as some of the smaller, shorter segments that are identified as being sort of remote and by themselves. And so for each of these, it allows you to turn off and on the different data set layers. Here in this case, we're sharing, again, we're sharing KMZs with the district staff in order to use this to prioritize the corridors that they're interested in. And to do that, we created a combined layer, which we called roadway type. Essentially, this is any location where any of the potential countermeasure segments were identified, to see if they could address this more on a corridor basis and not countermeasure by countermeasure. And finally, as I showed you on the spreadsheet, we have the data layers there for our PSI segments and corridors. As you can see here, there's a few red corridors identified here in this section just south and west of Richmond. So in essence, they could see if those segments overlapped, being adjusted for volume in terms of being above average. So to wrap up, where are we headed with this? We are at the point now where we have shared this information in the past few months with the intent that the districts focus on what we have designated here in Virginia called the corridors of statewide significance. And so these corridors are a subset of our national highway system and are predominantly all of our interstates and parallel primary system. If there is not an interstate serving that market sector of the Commonwealth, then like the green line across the bottom is US 58 is identified as a corridor, as is the east-west blue corridor of US 460. And so these main routes will be our focus, predominantly to look at where we can do those lower cost systemic traffic control devices, but also look at where we may need to have some more corridor-based, higher cost, more benefit cost-driven shoulder widening projects. So we've developed templates for our field staff to use and essentially looked at the MUTCD and different countermeasures that are out there to determine what are the minimum requirements moving into a second and third tier of enhancements for traffic control, shoulders, rumble strips, and so on for different locations along the network. As they do their field reviews, then they can refer back to these templates where everything is essentially in a one-stop shop for looking at those treatments. So here you see our curve template for divided highway and non-limited access. We have similar templates for two-lane roads and for our three-way limited access facilities. And with that, I'm going to leave it there. The other thing that we do have ongoing that I do not have a slide for, though, is we've been able to reinitiate our friction monitoring program with this information, and we're sharing the high friction surface segments, which are clusters of wet crashes, with our materials and our pavement folks in order to go out and conduct skid tire testing surveys of those locations to help with our problem identification there as well in terms of the pavement surface. And so with that, I will close and give it back to Rob for questions and answers.
Well, Stephen and Scott, excellent presentations and a lot of questions. So we're going to jump right into some of these. Scott, just as kind of a start on this, there were a number of questions related to the criteria that you used as it related specifically to transit and your shoulder widening. And so I was wondering if you could address things like why the 6-foot shoulder, why a mile from a transit stop. There were some who felt like that should be wider on the shoulder and closer. You know, that once you get past a half mile, it's difficult, or the usage really drops as it relates to transit. So could you talk about the criteria you used for coming up with those numbers?
Sure. The 6-foot and this transit criteria were both driven by considering bike connectivity and usage. It's really not optimal to sign or provide a bike facility that's less than 6 feet wide, and so the 6 feet threshold was based off of if you're going to stripe a bike lane or just provide a shoulder as a bike facility to provide that buffer for traffic. We did screen the entire network using ADT functional class and posted speed, and we actually screened the entire network for all the shoulders that were deficient using AASHTO Green Book criteria. So as we know, some facilities require by AASHTO a shoulder greater than 6 feet, but considering our limited resources of funding, we weren't going to take a 6-foot shoulder and increase it to a 12-foot shoulder when we have so many sections of roadway that don't have any shoulder at all. The mile from a transit stop, I realize that the rule of thumb for if a pedestrian is making a transit connection is more like a quarter mile. But again, this was assuming multimodal. So it was not only trying to accommodate pedestrians, but also, again, those bicyclists making transit connections to and from transit on a bike as well.
So these were not optimal, but these were, what's a good starting point? What do we want as our baseline? Is that fair?
Exactly, yes.
Okay, very good. Stephen, a number of questions related to the types of countermeasure strategies, and one of the questions is, what tools did you use to assist in selecting your various countermeasure strategies once you had done your initial analysis?
So the selection of actually what gets put in for each of those identified segments and corridors is really the purview of the district traffic engineering staff working with their designers and their planners in terms of looking at the bicycle accommodation issue. And so the list of countermeasures there has been fairly well developed by Federal Highways and their contractors, and primarily relying on NCHRP Report 500 series and some of the newer advancements that have happened since those were published here several years ago. And so the list of countermeasures has kind of been well known for quite a while, and now it's up to the districts, in our case being decentralized, to identify what exactly they want to do in terms of applying this sort of cafeteria of countermeasures.
All right, so Stephen, one of the questions that just came in said, the Utah focus seems to be on a proactive approach. So it's examining the system using the Lidar type tools, and then in that analysis, regardless of where the crashes are occurring, just kind of having a sense of risk factors and moving in that direction. The question is VDOT also looking at systemic improvements based on the road deficiencies using a more of a systemic approach? And then it says, this seems valuable in addressing the 22% of crashes on mainly secondary roads.
Right.
Your chart showed as kind of, it's random. So
right.
How would you address that?
Well, we know that we can't build our way out of the roadway departure problem. That we have to pretty much address what we can do on the roadway itself or with traffic control devices. And so, Scott did have, part of his scoring was crashes. In our case, we were looking for a crash threshold, primarily to look at, those segments that have curve issues, which curves along a corridor has an issue. But what I've been trying to preach to our district folks is that you don't want to go out and just address one or two curves along a given route in a given county, that you want to be more holistic, that although we, with this window approach, identified given segments along a route, that you would look at the whole route in terms of what you can do with this list of countermeasures. And so the intent would be to go out and do roadway safety assessments, starting with those corridors of statewide significance, to make sure that those are in the best condition that we can get them in terms of systemic treatments, and then working our way down into those secondary roads.
All right. If someone wanted to get a copy of your tiered enhancements template, could they? Is that publicly accessible?
Yes. Yes, they could. They
emailed you. Could you help them?
Most definitely. We're just setting up an external SharePoint site, and there's other ways we can get the data out to folks. All
right, Stephen. There's a question about the wet accident crashes and that type of an evaluation, saying that it seems like that was used as a focus. I'm going to guess that that's from the presentation. But since wet accidents only are about 15% of accidents, did you consider a broader criteria as related to pavement friction?
Yes, absolutely. What I didn't mention was that for those, so we looked for those clusters of the wet crashes, and that's what our old legacy mainframe database did for what we called our wet accident reduction program, or WARP. And now, as we're moving into this GIS world, we're using this as our first data set to look for those clusters of wet crashes. And of course, those could happen at an intersection, on a tangent, or on a curve. In this case, we're only looking at that subset of roadway departure wet crashes. So, taking away all of the other collision types as a filter right off the start. The other thing that we did do in looking at the data is identify the curves that had a higher threshold of crashes. In other words, which segments had curve crashes, as identified by the police officer, that met a higher threshold. And so for a lower threshold, we would look at traffic control devices, for example, markings and delineation. Well, for the higher crash threshold curve segments, we would also request that they look at the pavement condition and pavement friction. And so both of those data sets were flagged and given to our pavement folks to go out and do the skid testing this year.
We certainly seem that, at least on the horizontal curve, which is what we still have up on our presentation window here, that high friction surfacing, for example, would be a much lower cost than your typical reconstruction from a systemic standpoint. So it's interesting, the new tools that are coming into the toolbox as it relates to those types of crashes. I have there's one of the questions here I think is excellent. I'd like both of you to address that if you would. It says, once the roadways have been improved, will there be a feedback loop to determine if the safety measures have increased safety on the roadways? I think that's an excellent question. I think sometimes, not just as it relates to safety, but in a lot of our projects, we're great at doing the pre-analysis, but there's not a lot of post-mortem done on projects, whether it's operational or safety. So would either of you address that, or both?
If the money that's funding the project comes from federal highways, from the Highway Safety Improvement Program, we're actually required to do a before and after study. And so here in Virginia, what we do is we look at both total crashes before and targeted crashes. So for the roadway departure question, we would look at total crashes along these corridors, as well as the targeted roadway departure, and by severity, so that we could see how we're doing in addressing those goals and targets for our strategic plan. So that data is collected each year, and and given to submitted to federal highways, as well as our partners to make sure that the district folks are seeing that they're identifying the correct locations as well. The other thing that we just recently started to do, in fact, we're just scoping on doing this now, is asking our district folks to also do a before and after on a targeted number of construction and maintenance projects, some of the larger projects perhaps, so that they can see what the effectiveness has been in terms of safety for those. And part of that is a little bit self-serving because we have a new code here in Virginia that's requiring us to prioritize state-funded projects. And one of the measures that we're using to prioritize is the safety effectiveness, the crash modification that's going to result from those projects. And so we want to develop a database of larger construction projects that have many, many treatments included in them to develop crash modification factors for those.
Great. Scott?
Yeah, I'll just add, I concur with Steve. We do the before-after analysis on our HSIP program. We do a 3-year before and after. That becomes very problematic, though, with our move to systemic treatments because we're targeting areas that may or may not have an initial crash history. And so our measure becomes a little bit more nebulous where we're reporting the statewide change in the targeted crash type that's targeted by the systemic treatment, but we can't necessarily tie the change in roadway departure, for example, to a specific project at a specific location. I will also mention, Steve opened the door to this, there is a statewide push. MAP 21 federally also requires more safety plan more safety consideration in the planning process. I'll just throw a bomb out there and walk away, but I'm going to suggest here that the old DOT adage that if we rebuild a road, it's improving safety because we followed all of the AASHTO Green Book design standards, it may be proven a fallacy. Just because we're following all of our design standards may or may not mean that a given project, in fact, improves safety. And so our areas that we're going in our analysis tools here with the identifying roadway features and roadway conditions that affect safety and crashes may lead us to a change in some of our design standards, which I'm excited about that conversation and what's ahead. Because
we could almost spend an hour on that one question, so you're right. We probably ought to. We got about 10 minutes, so we wouldn't want to drill too hard into that one. But that's a very interesting point. Let me ask, Scott. Well, first of all, I would imagine that's particularly true as far as the before and after. Your earlier comments on the before and after, when you're looking at things like cycle or bicycle corridors, because you don't have a lot of before or after crashes, and 1 or 2 crashes could really alter your numbers there. But let me ask you, as it related to the bicycle, of all the things you could have focused on with these data sets, one of the questions is, was the bicycle focus for a specific reason? Was this part of the national bicycle corridor and you were asked to take a look at that? Or why the bicycle piece of this compared to others? Was this a political consideration? What motivated you to pick this as a project to look at?
That's a great question. The active transportation has become a new focus of the DOT recently. We have a new director that's focused that way, and he's really pushing a culture shift internally at the DOT. But I want to emphasize that although we promoted the benefits to the bicycle community in our analysis, we really were targeting a multidisciplinary approach to widening shoulders benefits bicycle users as well as reduces roadway departure crashes, improves our freight corridors. So all of those other weighting criteria we put into the analysis was very intentional in that widening shoulders targets all of those types of crashes and roadway users.
Fantastic. All right. We've had a couple questions on this, and so Stephen, I'm going to throw this out to you. The question is your PSI calculation including empirical bays to account for RTM?
Yes, it's the full-fledged safety analyst approach, looking at each of our roadway inventory links for expected crashes and adjusting that. Yep.
All right, let me answer this because we're getting a couple of questions on this. I will be, for all of you who registered for the webinar today, I will be sending you out the PowerPoint presentations and contact information for both Scott and Stephen. So you will be receiving that. So you don't need to worry about how to get in touch with them because we will take care of that. We'll get that information off to you. There's one of the questions, and I think this is for both of you, is can you provide an example of kind of a typical process in investigating specific locations? I know, Stephen, you put a lot of emphasis on when you looked at a region, you saw a lot of hot spots. But when you're seeing high crash locations, whether it's road departure, wet weather, whatever, where do you begin in that process of trying to determine causality? Are you looking at the numbers? Are you going out and physically looking at sites? What is or maybe even how has the process changed as well over the last few years?
Sure, that's exactly what's happened. Here in Virginia, what we've actually spent a lot of time doing for these corridors of statewide significance as a starting point is develop what we're calling a hybrid roadway safety assessment. And so when you're looking at miles and miles of roadway, you don't have the opportunity to do a very detailed engineering assessment. And so what we've developed is a methodology that uses a video and GPS that will allow us to tie that video back to our linear referencing system and our crashes and our assets, so that we can basically video the corridor with a team of experts in the van, and then go back to the office and do the roadway safety assessment from the office. And so that ground truthing is coming from the video. We found that to be a little bit more effective than using the video logs that our pavement management vendor produces. And not only that, but it allows you to tie information from that video that's more, what shall I say, is a better assessment of actually driving that corridor from a human factors perspective. With that continuous video, you can actually look at the other attributes of the road beyond where you have those crash clusters or where you have your curves and so on, to see what other combinations of the roadway alignment and the physical environment are impacting the safety. And so we have developed sort of a template for that, and we're about ready to share that with our districts as one of the methods they could use to assess these corridors.
Scott?
I would just speak to the example I gave today as being indicative of when somebody says we have a problem here, our first reaction is now, well, let us research that problem at that location and compare the same problem to similar locations around the state. And the data and the analysis tools we have help us to make that comparison a lot more efficiently and quickly than before, where be a daunting task of trying to collect data from similar sites throughout the state. So we're certainly moving to an area where although we need to address the hot spots, we're becoming a lot less reactive and a lot more proactive than we used to be.
Scott, I saw a presentation, or know that there was a presentation at TRB about I think Brigham Young University had developed an algorithm that allows you to look at your data sets, or your mobile LiDAR data sets, and actually be able to calculate curve radius out of those data sets. Are some of these new tools and these new data, systemic data pieces, are you still learning how to apply them and how to maximize the value of that, or are there any examples of how some of these new data sets are amplifying your analysis?
So boy, we could talk another hour on that one too, Bob.
Well, maybe we ought to hold off on that one.
But let me just mention we're finding new ways of using the data every day. And one of the reasons why safety was at the table of our initial data collection effort, and HSIP funds paid for about a third of the LiDAR data collection, was we recognized the ability to feed that roadway data into a Bayesian crash predictive model. And that's something that BYU has built for us and part of our overall picture of where we're going with the data.
Well, then I have a question for both of you. It would seem like that we are now at a time where we have so much data that and only so many hours in the day. So have you begun to think about how do we address those types of issues, as far as, are there things that either organizations or case studies or analytical process pieces, white papers, those types of things that would be beneficial in systematizing this approach, that either to maximize the value of all the different tools that you're using, or to allow states and even local agencies to share how they're using these data sets? Any thought as far as how we amplify the value of this, given that you now have so much information but so little time to actually really drill into it?
I will answer it this way, from the Commonwealth's perspective, that our traffic and safety professionals in the district do not have time to get into these data sets unless they're made extremely user-friendly. They just don't have the time nor the expertise set to work with large databases and GIS files. And so we've been providing that as a service. We are decentralized, so that fits very well with our business model, in the sense that we're providing policy and information for them to make the right decisions. So, yeah, for example, our roadway alignment data that we have on our interstate and primary system, it's there, it's available, but you need to be a pretty good GIS person in order to pull it up and look at it and analyze it for a given corridor and so on. So we're looking for ways to better, integrate that into our enterprise data set and so on, as Scott has been able to do with the LiDAR-based sort of full meal deal data collection. Ours has been a little bit more one piece at a time. So that is an issue, and we look to others and try not to reinvent the wheel.
Well, gentlemen, let me say this. This is about the fastest 90 minutes I think I've had in a long time. A lot of tremendous information. And on behalf of GTMA, I want to thank you both for the presentations. I'd like to remind those who have watched the presentation today that we will be uploading the presentations to our GTMA YouTube channel, so you'll be able to watch the presentations there. In addition, I will be sending out links where the recordings can be watched through the GoToWebinar process. So if you have those who you know who should have watched this today but didn't, we will be sending out follow-up of where you can go to watch the recordings. And I'd like to thank all of you for your questions and your participation today. And with that, we will end the webinar. Thank you all, and have a great rest of your day.